Lesson 11-6, Similar Triangles and Indirect Measurements. And in this lesson, you learn to identify corresponding parts and find missing measures of similar triangles, and to solve problems involving indirect measurement by using similar figures. Okay? So let's take a look at this example. Have you ever used a copy machine to make a reduction or enlargement of something? The original and the copy are the same shape, but they are in different sizes. So in math, you call this dilation. And we can use graph paper to investigate the relationship of such two figures. Basically what it's saying, let's say you have this original portrait right here, and you want to reduce this using a copy machine. This is what we call a dilation. So on graph paper, you can take it out, and you need a straight edge also as well. Draw and label a triangle on the coordinate plane, very similar to what I'm going to do, but it's up to you what kind of triangle you want to draw. So this is an example. This is triangle ABC. Okay, so from there we go to step number 2. Multiply the coordinates of each vertex by 2. Draw the new triangle. Okay, so if we go back to our triangle ABC, the vertices are 2, 2, okay, negative 1, 1, and 4, negative 1. And if I multiply, for example, vertex A, okay, which is vertex A is 2, 2, okay, and it says there, multiply the coordinates of each vertex by 2. So if I multiply this by 2, I'll end up with coordinates 4, 4. So I'm going to do that with 1, negative 1, and 4, negative 1. And if I do the same things, okay, if I multiply them by 2, this will become 2, negative 2, and this will become 8, negative 2. Okay, so if I plot this again, look what happens. Okay, I have 4, 4, which is here. Okay, and I have 2, negative 2, which is right here. And I have 8, negative 2, which is right here. Okay, so that's my new triangle from triangle ABC, and let me name this triangle, okay, A prime, B prime, and C prime. Okay, now look at this one in letter A. Going back here, once we have this, okay, we start to measure. Let me get that so we can bring it to where we are now. So let me get this whole thing, and then let me put it back here. Okay, right there, and obviously we can make it smaller because it's too big. So if we get that, let's put it down here. Right there. So we'll do right there. Okay. There you go. So you put down there, measure the angles in the two triangles. How do they compare? I'm not going to measure it for you, but you'll find out. Once you measure angles, angle A is congruent to angle A prime. Okay, angle C is congruent to angle C prime, and angle B is congruent to angle B prime. Okay, and use a ruler, okay, to measure the size of the two triangles. Write the ratio comparing the measures of the corresponding sides. Okay, what do you notice? Okay, so if I measure this with a ruler, you will find out that the ratios are the same. So they have the same ratio. For example, AC will be equal. AC is equal to A prime and C prime, the sides, that is. Okay, so if we repeat the activity by multiplying the coordinates of the original triangle now by 1/2, so if I, instead of multiplying it by 2, I multiply it by 1/2 or divide it by 2, Are the results the same? Of course, the answer would be yes. The results would be the same. Okay. So what do you notice in these triangles? Okay, they have the same shape, but they have a different size, which brings us to similar triangles. Well, I think it's down here. Okay. Similar triangles. Let's see if it's down here. No, it's not. Okay. So the triangles you drew in the activity were called similar, figures that have the same shape but not necessarily the same size, like this one, okay, are similar figures. Okay. So when you talk about these two triangles, let's even change the name of these to the other triangle so we won't be confused with the prime. Let's make this D, E, F. Okay, so we'll change it to triangle DEF instead of A prime, B prime, and C prime. So if you look at that one, triangle ABC, okay, triangle ABC is similar to triangle, this is the symbol for similar to, triangle DEF. And if you notice, my vertices are correspond to each other. Okay, so they're similar to each other, and if you measure the angles of angle A, angle A would be congruent to the measure of angle D. Angle B will be congruent to the measure of angle E, and angle C will be congruent to the measure of angle F. Okay, even though they have different sizes, they have the same shape. Okay, the angles, okay, are still very much equal to each other. The corresponding angles are congruent to each other. Okay, which brings us to corresponding angles of similar triangles. If two triangles are similar, then the corresponding angles are congruent. Okay? So, it is also true that if the corresponding angles of two triangles are congruent, then the triangles are similar. We will use this property in example 2. It's coming up later on. Okay, the corresponding sides of congruent triangles also have a special relationship, and let's take a look at this figure below. Triangle LMN, okay, is similar to triangle RST. That means in this case all the corresponding angles are congruent. So we can compare the measures of corresponding sides by using ratios. Okay, let's take a look at the ratios we can compare. So when you talk about corresponding sides, LM corresponds to RS. So the measure of segment LM over the measure of segment RT, okay, LN over the measure of segment RT is equal to 6 units over 18 units, or 1/3. Okay, because LN and RT are corresponding sides. So let's take a look at another two more corresponding sides, and that is measure of segment MN and over ST. If you notice, okay, the numerator starts with the small triangle, the denominator is the big triangle. Okay, so all the numerator is the small triangle. The denominator, I'm sorry, is the big triangle. So you have LN, small triangle, RT is big triangle, MN is small triangle, ST is your big triangle, and you need to be consistent to be able to find that they are all the same. So if you notice here, segment MM, the measure of segment MN over the measure of segment ST would be 3 units over 9 units, or still 1/3. And let's take a look at one more pair of corresponding sides, and that's LM and RS. So again, the numerator is our small triangle. So the measure of segment LM over the measure of segment RS, okay, is 5 over 15, or still 1/3. Okay, you notice that the ratios are equivalent. So the corresponding sides are proportional to each other. This example and the activity at the beginning of the lesson seem to suggest the following, okay? And this is what we come up with, that corresponding sides of similar triangles, if two triangles are similar, then their corresponding sides are proportional. Okay? So if they are similar, the sides are also proportional. It is also true that the corresponding sides of two triangles are proportional. Uh, then the triangles are similar. Okay? So the reverse is also true. If you have corresponding sides that are proportional, then you can conclude that the triangles are similar as well. So let's take a look at example number 1. Okay, if we have triangle GHI is similar to triangle JKL, GHI, JKL, find the value of X. So we want to find the value of X, which is segment KL. Okay, so we write a proportion, okay, shown using the known figures, which is right here. Nope, it's not there. Oh, guess not, so I need to write it over. Okay, so we need to write a proportion for this. Okay, we know that the measure of GH, side or segment GH, okay, it corresponds to side JK. So the measure of segment GH over the measure of segment JK, okay, is equal to, we start with a big triangle because we started from the big triangle in this particular ratio right here, the measure of segment MH, measure of segment, sorry, HI, not MH, okay, HI corresponds to KL over the ratio of segment KL. So if we substitute the values, measure of segment GH is 12, the measure of segment JK is 4, is equal to the measure of segment HI, which is 9, and this is what we want to find out, the measure of segment KL. Again, all we need to do is do cross products, so this becomes 12x equals 36, 9 times 4, and we divide both sides by 12. Divide both sides by 12, we end up with x equals 3. So the measure of segment KL is 3 centimeters. Okay? That's example number 1, and let's take a look at example number 2. So in example number 2, we have this. Let's see if this is going to come out here. Nope, I need to do it again. So let's do this. So use the information in the figure below to find the value of X. Okay, since vertical angles are congruent, remember what vertical angles are. So these two are vertical angles. Okay, the measure of we know for a fact if we're going to vertical angles being congruent, that angle ACB, which is this angle right here, is congruent to angle DCE. Okay, DCE. And if you notice, the vertex is the middle letter where A and D are corresponding angles, B and E are also corresponding angles. Okay, and what did we find out? We found out that angles A and D are congruent because of that hash mark, and angles E and D are also congruent because they are both right angles. So what do we know? If all angles are congruent, then we know for a fact that triangle ABC, okay, we know that triangle ABC is similar to triangle DEC. And be very careful about this when you say triangle ABC. Okay, ABC, okay, is similar to triangle DEC. DEC should correspond to the angles of ABC. So you have angle A and angle D are corresponding angles. Angle B and angle E are corresponding angles, and obviously they're both angle C right here, so they also correspond. So we know that they correspond to each other. Okay, we know for a fact too that the measure of AB, the measure of segment AB, when we find out that they are similar to each other, okay, over the measure of, meaning we want to find the side that corresponds to segment AB right here, and the side that corresponds to segment AB will be segment DE. Okay, so that's one pair of corresponding sides. We know for a fact that if that's the case, okay, all of the corresponding sides are in proportion. So we have measure of segment BC. Again, we start with this triangle, okay, over the measure of segment EC. Okay, so from there, okay, we can now substitute values. We know that AB is 10. We know that DE is X. BC is 7.5. And EC is 12. Okay, using cross products. Okay, so if we do cross products, so basically, did not mean that one. So you multiply 10 times 12, and then you simply multiply 7.5 times X. You end up with 10 times 12 equals 7.5 times X, or 120 equals 7.5x. Then we divide both sides by 7.5. Okay, divide both sides by 7.5. We find the value of x as 16. Okay, so the measure of segment ED in this case is equal to 16 feet. Okay, and we can also use indirect measurement to do this for similar triangles. What does that mean? So you can use what you know about similar triangles to find the measure of the objects that are too large to measure directly, as shown in example 3. This kind of measurement is called indirect measurement. And let's take a look at example number 3. Okay. So in example number 3, in ancient Egypt, mathematicians used a technique called shadow reckoning to determine the height of tall objects such as pyramids. The height of the staff and the length of a shadow are proportional to the height of an object and the length of its shadow. The objects and their shadows form two sides of similar triangles. Use shadow reckoning to find the height of a flagpole in the figure below. So what is it saying? So to be able to find the height of a flagpole, they use in ancient Egypt a small staff, which is 1 meter long. Okay, and if you notice, it forms two similar triangles. And we know for a fact if the angles of these two triangles are congruent, the sides are also proportional. So basically, we can find the height of the flagpole by using a similar triangle like the one formed with the flagpole. Okay, so if you use a meter stick and look at the shadows, okay, where the length of the shadow and the height of the meter stick, we can find the height of the flagpole. So what do? Okay, first, we know that the length of a meter stick shadow, okay, over the length of the flagpole shadow, because those are your two corresponding sides, will be equal to the length of the meter stick, okay, length of the meter stick over the length of the flagpole. So this is the length of the meter stick, and that is the length of the flagpole, because these two sides correspond to each other. Okay? So from there, okay, we simply create a proportion. So we substitute the values of a length of a meter stick equals the length of a meter stick shadow over the length of the flagpole shadow equals the length of the meter stick over the length of the flagpole. So we substitute the length of the meter stick shadow, which is 0.7. We substitute the length of, make it a lot longer, length of the flagpole shadow as 5.6. Oh my goodness. Do that again. 5.6 is equal to the length of the meter stick, which is 1 meter, over the length of the flagpole, which we want to find out, which is h. Okay? And we do cross product, so this becomes 0.7h equals 5.6. Then we divide both sides by 0.7. Okay? And then we end up with h equals 8. Okay, so 5.6 divided by 0.7 is 8. So the flagpole is 8 meters high. Okay, and that's how you use indirect measurement to be able to find the length of a tall object. So in this case, it's a lot easier to do indirect measurement than for you to climb a flagpole with a measuring device. So the indirect measurement works, and the ancient Egyptians found that out very early on. And the secret word for this particular lesson would be corner. Secret word is corner. Thank you for watching.